Okay, we're going to look at force 6.2, which is essentially Newton's second law. If you recall, force 6.1 was Newton's first law and focused a lot on the concept of balanced forces. Balanced forces resulting in no acceleration, which we now understand could either be standing still or at rest, and constant velocity or constant motion. Force 6.2 asks you to explain that the rate at which an object changes its speed or direction, aka acceleration, is proportional to the vector sum of the applied forces, or the net force, F net, and inversely proportional to the mass. Explain the relationship between acceleration, net force, and mass. Now, I first want to talk about net force. They call this F net. And this is really important in Newton's second law because F net means all of the forces acting upon the object. So that means maybe we have gravitational force, we have normal force, we have an applied force, we have frictional force. So what we're looking at here is maybe an object that has a normal force and a gravitational force. Let's say this is just maybe an object like a box being scooted along the floor. And in this case, since the object isn't going up or down or accelerating up or down, then the normal force and the gravitational force are going to be equal. They're going to be balanced, or they're going to cancel. Let's say, though, that we have an applied force, and we obviously also have our frictional force since we're scooting this box along the floor. And we have an applied force that is greater than the frictional force. So perhaps we have positive 20 newtons of force applied, and we have negative 5 newtons of force as far as our frictional force goes. As far as our F of G and F of N, since they're equal and opposite, it doesn't necessarily matter what the values are since they're going to cancel each other out. So we're going to leave those alone for now, and we can look at those a little bit later. So this particular object has positive 20 newtons and negative 5 newtons. So we know that the net force acting on that object is positive 15 newtons. So the only number that we're really concerned about here as far as Newton's second law goes is that positive 15 newtons. So it is essential that we figure out exactly how much force is acting upon the object with all forces taken into consideration. So coming back here, once we figured out that net force, we can understand a little bit more about Newton's second law. So if you recall at the beginning of the year when we were talking about a Newton, we talked about the F equals ma formula, and we said that F is our newtons, and that's our force. And in this case, that's going to be our F net. So all forces acting upon the object. This is our mass. And this is our acceleration. Now, up until this point, we've talked about the acceleration in terms of gravity because we've just been using our constant force of gravity. But when we talk about Newton's second law, we could be talking about the acceleration of an object, say my box that I'm pushing along the ground or scooting along the ground. I would then be able to calculate that object's acceleration, knowing the object's mass, and knowing the object's F net or net forces acting upon the object. So really, Newton's second law is kind of the mathematical component to understanding forces acting upon an object. And they want you to really focus on this relationship between force, mass, and acceleration. So the first part says to explain that the rate in which an object changes its speed or direction or changes its acceleration is proportional to the vector sum. So what the heck does that mean? Basically what that means is if my force gets increased and my mass stays the same, my acceleration will be increased. Meaning if I push something with more force, it's going to accelerate at a greater rate. I think that that makes a lot of sense. And you're going to be doing a little experiment using 3 mass balls or 3 mass spheres, and you're going to be blowing force using a straw. So you can kind of look at really what does this relationship look like. So these guys are proportional, meaning if I decrease my force on the same massed object, I'm going to decrease the acceleration. Again, less force, less acceleration. That totally makes sense, and I think we probably already kind of understand that concept. The second part, however, says that the speed or direction, the acceleration, is inversely proportional to the mass. So if I increase my mass. So my force now is going to remain constant. I'm pushing with the same amount of force, but I increase my mass. My acceleration then is going to actually decrease. Think about a bowling ball and a tennis ball. If I apply the same force to the bowling ball, which has a greater mass, it's not going to accelerate as fast as the tennis ball. So that also means that if I'm looking at the tennis ball and I decrease my mass, then my acceleration is going to increase. So that really is your relationship between acceleration, net force, and the mass of an object. The force and the acceleration are directly proportional. As one goes up, the other goes up when the mass is the same. As far as the acceleration in the mass, as one goes up, the other goes down, meaning they are inversely proportional. And that, in a nutshell, is the relationship between force, mass, and acceleration for force 6.2.